Hydraulic systems transmit and control energy or power through the use of moving and pressurized fluids. When man first learned how to exploit water power to turn millstones and power pumps, he had taken the first step towards industrialization. Nowadays, the use of hydraulics as a power medium is widespread throughout many different industries. In fact, usage has expanded to such an extent, today very few industries would be able to survive without hydraulics. Many of us drive cars, and each time we brake, we make use of the vehicle's hydraulic system. This is what happens. When the brake pedal is pressed down, a hydraulic cylinder is influenced which raises the pressure in the braking circuit. This increase in pressure is in turn transmitted to the brake cylinders, which activate the brake shoes, forcing the vehicle to a standstill. The fluid in the circuit therefore has the ability to transmit a force. What is meant by a force? By force, we mean that which can either create or change movement of a body. The law of inertia dictates that an immobile object cannot move by itself. If force is applied to an object, it can then move in either of two directions. Since we know that a fluid in motion has the ability to transfer power, it is also possible to replace human force with the aid of a fluid and move an object as easily or even more easily than by using physical exertion. If we replace the human braking force with a fluid, we will achieve the same effect. How? The answer is to be found in the characteristics of the fluid used. The fluid is non-compressible. In other words, it cannot be compacted or decreased in size. This is a bottle which has been completely filled with a fluid. If the cork is pressed down even further into the fluid using relatively light pressure, the bottle will ultimately explode. The reason for this is that the pressure inside the bottle spreads in all directions. Since this pressure is uniform at all points inside the bottle, a large force will be created over the entire inner surface of the bottle. A corresponding phenomenon occurs within the technology of hydraulics. In this case, it is a fluid which creates a substantial increase in force. If you compare these two illustrations with the previous one, you will notice that the lever arm has been replaced with a fluid system, where the different levers are represented by two different surfaces. As you can see, the right-hand piston area is twice as large as the one on the left. The cylinder shown here has been subjected to a load of 1,000 kilograms. This load is evenly distributed over the entire piston area of 100 square centimeters. This means that every square centimeter is subjected to a load of 10 kilograms. The force per surface area of hydraulic fluid is what we term pressure. Pressure is usually measured in MPa, megapascal. However, older units of measurement, such as bar and kgp per square centimeter, are still in common use. The table shows the differences between these units. The figures given on the same line correspond to each other. If we look at the coloured line, we will see that 10 MPa corresponds to 100 bar or 100 kgp per square centimetre. Let's now study the function principle of a constriction in a hydraulic system. The inward cambered part, or constriction, in the pipe serves as a throttle. This causes the entrapped fluid to move in whirls, so-called turbulence. Constriction also generates heat. This sketch shows that the pressure on both sides of the constriction is equal. Consequently, there is no movement of the fluid. If the pressure on one side is higher than on the other, the fluid will start to flow towards the side with the lower pressure. If we continue by mounting a throttle valve in the line, we can alter the size of the passage through which the fluid will flow. When the valve is fully open, the fluid can then flow from the pump totally unhindered. A pressure gauge mounted on the line shows the pressure reading is 0. When the throttle valve is threaded down, pressure is required to propel all the fluid delivered by the pump. The passage in the valve narrows, and the pressure gauge gives a pressure reading. If we continue to thread down the throttle valve and make the passage in the line even narrower, the pressure will increase even more. When it has risen to a specific level, something must happen. Either the pump, the pipe, or the valve itself will fracture or burst, unless the pressure is reduced once more. The point here is that unloaded pumps do not provide pressure. They merely supply a volume flow, usually stated in litres per minute. A modern hydraulic pump is capable of supplying a more or less constant volume flow independent of the pressure. Pressure is generated through loading, and here it is achieved through constriction. What happens if the load is in the form of a weight? If we remove the weight, the pressure will drop. Consequently, it is not the pump that supplies pressure. This is the same system shown to you a few moments ago. When we adjusted the throttle valve, we increased pressure. We also mentioned that if the pressure is increased too much, then something is bound to happen or break. To avoid this, it is common to install a pressure limiting valve in the system. This valve contains a ball or poppet, which is spring-loaded against the pressure. It seals against a seat. When the pressure becomes so high that the spring force is no longer able to resist it, the fluid starts to flow through the pressure limiting valve and back to the tank. The pressure will not increase further, even if the throttle valve is threaded down even more. Will the valves function in a similar manner when they are parallel connected or series connected? The answer is no, and this is why. When several pressure limiting valves are connected in parallel, in other words, next to each other, the valve which has the lowest pressure setting will determine the system pressure. In this case, valve A is set at 10 MPa. Another valve, B, at 12 MPa, and the third valve, C, at 15 MPa. Now, let's connect the valves in series or one after the other. In front of and behind each valve, we connect a pressure gauge to see what happens at the various stages along the line. The pressure limiting valve nearest the pump is set at a pressure of 15 MPa, followed by the next valve set at 12 MPa, and the last in the line set at 10 MPa. Now study the pressure gauges from right to left. The gauge furthest to the right shows the atmospheric pressure, in other words, the pressure of the air we normally breathe. The next gauge gives a reading of 10 MPa and the third a reading of 22 MPa. This is easily explained by adding 10 plus 12, which equals 22. At the same time, it's not hard to work out that the gauge nearest the pump will give a reading of 37 MPa, since 10 plus 12 plus 15 equals 37. Consequently, when pressure limiting valves are series connected, pressure is added together. A hydraulic fluid flows in a cylinder that holds 10 litres when filled completely. If the pump delivers a flow of 10 litres per minute, then the cylinder will be filled within 1 minute. If instead the pump delivers 20 litres per minute, then the cylinder will become filled in half the time. In other words, within 30 seconds. The speed of the cylinder piston is therefore determined by the volume of fluid flowing to the cylinder per time unit. This can be measured in litres per minute. No matter how far the piston lifts, the velocity remains unaffected. It is therefore the volume flow of fluid that determines the velocity. The speed of the piston is also influenced by the diameter of the cylinder. Here are two different size cylinders. If these are connected to individual pumps that are of identical size and which are started at the same time, we will soon notice that after a short while they have moved different distances. The larger cylinder piston has moved only a short distance, while the piston in the smaller cylinder has completed its full work stroke. We have now advanced to the stage where we can study a simple hydraulic system, note its composition, and see how such a system works. The valve is activated so that the piston in the cylinder moves in the direction of the arrow. The pump supplies fluid to the plus side of the cylinder, the red section, and the piston starts to move in the desired direction. The minus side of the cylinder, the blue section, is also filled with fluid. Due to movement of the piston, the fluid is forced out through the blue line to the tank. When the cylinder reaches its end position, the fluid has nowhere to go. This could then result in something fracturing unless specific measures are taken. A pressure limiting valve has therefore been mounted in the system to prevent this happening. The entire flow of fluid now passes through the valve and back to the tank. If we now want the piston to return to its original position, then the volume flow from the pump should now move to the minus side of the cylinder. This entails connecting the plus side to the tank so that the fluid can flow back. This is achieved with the valve shown. When the piston has reached its end position, further movement can be terminated without switching off the pump. It is now necessary to prevent the flow from passing by way of the pressure limiting valve back to the tank. This is done by moving the valve into the zero position. All of us at some time or other have struggled our way up a steep slope, and this man is obviously having great difficulty in reaching the top. It's hard work moving one's own body up a steep incline. But it's even more difficult to move a body rapidly up a slope or incline. This needs a much higher power source. With power, we mean the work capability per time unit. The faster a job is completed, the greater the amount of power consumed. If a man climbs a slope twice as fast as another, then twice as much power has been consumed. If this deck crane is to successfully hoist this crate 1 meter within 1 second, then it needs to generate a power capacity or work capability of 10 kilowatt. To enable the same crane to generate 10 kilowatt, the pump must also generate at least 10 kilowatt. In actual fact, the pump must generate a larger capacity than 10 kilowatt, since flow losses in the line, combined with valve leakage, absorb a small proportion of the initial power generated. By now we are all aware of the fact that a pump cannot operate without energy losses. Some of the pressurized fluid leaks back to the tank, and certain flow losses occur inside the pump. Also, some of the capacity is lost through friction between different components inside the pump. Leakage and flow losses are known under the common name of hydrodynamic losses, because fluids are involved. Losses caused through friction are termed mechanical losses. The degree or level of efficiency is a measure of how a component exploits the energy it generates. This illustration demonstrates the substantial differences that can occur between different types of pumps. Let's compare the two shown. They both generate the same capacity, namely 5 kilowatt. The pump at the top has a poor level of efficiency and therefore demands an installed capacity of 6.7 kilowatt in order to generate 5 kilowatt. The energy loss here is therefore 1.7 kilowatt. In contrast, the pump underneath has an excellent level of efficiency and only needs a capacity of 5.3 kilowatt. The energy loss for this pump is thus no more than 0.3 kilowatt. Now, answer the questions given in the Basic Hydraulics work booklet under the section Pressure Flow and Power. Basic principles of hydraulic systems. Closed circuits. Hydraulic deck cranes. Let's divide hydraulic systems into two categories or main groups: open circuits and closed circuits. This is a closed circuit complete with all related components. Let's continue by compiling a circuit containing only a few related components. Most of the hydraulic systems in Hagglund marine cranes use closed circuits. A closed circuit consists of a pump and a hydraulic motor that are interconnected with each other via lines. The pump has a variable displacement, while the hydraulic motor has a fixed displacement. An electric motor powers the pump. This is what an electric motor and a pump motor look like. When the circuit is operating, oil is pumped from one side of the pump to the other, and then through the hydraulic motor. With the variable pump, it is possible to vary the flow of oil and thereby regulate the speed of the hydraulic motor. With this type of pump, not only the direction of the flow of oil, but also the direction of rotation of the hydraulic motor can be alternated. If a circuit merely comprised these components, after a period of time, all the existing oil in the circuit would leak out because of the pressure. That is, higher pressure, greater leakage. Lower pressure, less leakage. To compensate for this leakage, certain components have to be installed in the circuit. A feed pump vacuums oil from a common tank for the circuit and also serves to keep the closed circuit full of oil. The circuit is filled by means of two check valves. A pressure relief valve limits the feed pressure to between 17 and 25 bar. The exact setting value for feed pressure is given in the instruction manual. All excess oil flows back to a common tank serving the entire crane. When the system is put into operation and subjected to a load, the main line, in this case the one on the right, will receive working pressure or high pressure totally dependent on the size of the load. The working pressure now closes the right-hand check valve. This results in a high and low pressure side in the closed circuit. The low pressure side is shown on the left and the high pressure side on the right. Oil from the feed pump must therefore be fed into the circuit via the left-hand check valve. The pressure in the left side, in the closed circuit, is now between 17 and 25 bar and is determined by the feed pressure relief valve. These two check valves consequently serve to separate the high pressure side from the low pressure side and enable refill of the oil fed into the closed circuit, irrespective of which side is under high pressure. The main circuit is designed to maintain a specific maximum pressure or maximum load. This pressure must be limited, however, to avoid bursting the system. Pressure in the circuit is limited by means of a main circuit pressure relief valve. When this valve opens, oil then flows from the high to the low pressure side, in this case from the right side in the circuit to the left. When the entire flow of oil passes from the pump through the relief valve to the low pressure side, the hydraulic motor ceases operating. A double check valve sharing a common spring is connected to the pressure relief valve and allows usage of a common pressure relief valve for both the right and left-hand sides of the circuit. Cooling. A shuttle valve has been mounted in the circuit to allow drainage of as much heated oil as possible from the closed circuit when the hydraulic motor and circuit are in operation. Let's start up the crane. When the electric motor and pump unit start operating, oil is fed from the pump via the shuttle valve to the pressure relief valve and straight back to the tank. When the circuit is operating, either a working pressure or high pressure is built up in the right-hand section of the circuit. High pressure now moves the shuttle valve to the left. The cooler inflow of oil is now fed through the left check valve and presses out the warmer oil to the cooler via the shuttle valve and the feed pressure relief valve to the tank. The cooler is here marked green. The valves shown earlier are collectively mounted in a common block, known as the unit valve. The luffing and slewing circuits with the closed circuit also have a unit valve, but lack the provision of feed pressure valves. On newer crane variants, for example the DS and G versions, feed pressure valves are not included with the unit valve for hoisting winches. Instead, feed pressure valves are mounted on separate valve blocks. Unloading the circuit when idling. Even though the variable hydraulic pump is set at 0 and therefore idling, in practice the pump still manages to supply a specific flow. This flow is sufficient to build up a pressure against the braked hydraulic motor. Despite a very small specific flow of oil from the idling hydraulic pump, a corresponding flow must pass through the main circuit relief valve. To avoid unnecessary heating of the hydraulic oil and resultant excess wear of internal components, the system must be unloaded. Unloading is carried out by short-circuiting the closed system by way of a motor valve. Motor valve function at low speed. With the hoisting winch operating in the low speed range, the motor valve spool is shifted to its proper position by pilot pressure at the same time as the motor brake is released. Oil is supplied to both motor connections A and B in parallel. The shock absorber valve. Pressure peaks in the circuit are taken care of by a shock absorber valve that forms part of the motor valve and which discharges a certain amount of high pressure oil to the low pressure side. This valve functions both in the normal, that is the low speed range, and in the high speed range. Motor valve function at high speed. The hydraulic motor may be operated at half its normal displacement by introducing a so-called two-speed plug to separate the A and B connections of the hydraulic motor. The motor will then run at approximately twice its normal speed, and the lifting capacity of the winch will be reduced to some 40% of the capacity in the standard speed range. By applying pilot pressure at the F connection, the two-speed valve spool is shifted to a position where hydraulic motor ports B and C are connected to each other. Hydraulic motor connection A will then receive the entire oil flow produced by the pump, circuit leakage accepted, and the motor will run at its double speed. Crane systems with 3 closed circuits. This is a simple illustration of 3 operative circuits: a hoisting, luffing, and slewing circuit. The circuits are positioned in the same sequence as in the hydraulics diagram. Together with the feed and pilot pressure circuit, they form a complete crane system. Pilot pressure circuits are not found on mechanically controlled cranes. How to identify hydraulic circuits in a hydraulics diagram? Hagglund's hydraulic deck cranes usually have a hydraulic system comprising 3 separate main circuits, namely a hoisting, luffing, and slewing circuit. Each main circuit is equipped with a hydraulic pump and a hydraulic motor. The types of pumps include variable axial piston pumps, vane pumps, and screw pumps. The motors installed are hydraulic, low-speed, high-torque variants of the radial piston type. All the high-pressure pumps are powered by a common electric motor by way of a gearing mechanism. A 4th circuit, the feed circuit, is also shown. Now answer the questions given in the Basic Hydraulics Workbooklet under the section The Application of Hydraulics in Deck Cranes.